Okay, so the first question that we have after you guys have completed your map. Coriolis forcing pushes the surface wind direction approximately 45 degrees to the right of the pressure gradient force. And this is, remember that this is in the northern hemisphere. In the southern hemisphere, it will push it to the left. Okay? So then it says, what direction is the wind blowing in from in these three locations? First location, Moscow, Idaho. Second location, Billings, Montana. And third one in Portland, Oregon. So based on whatever your resulting graph is, you'll be able to see the pressure gradient, and from there you can calculate where the wind is being diverted to, and hence where it's coming from. So I'm going to show you an example of an isobar map in Australia. So this one's going to be a little different because it's in the southern hemisphere. So the wind will be pushed to the left, but I think you will have the idea well enough in your head so that you can go ahead and finish this map, or rather this question, based on your resulting map for those three locations. Again, Moscow is going to be somewhere around here. Billings is somewhere around here. And Portland is somewhere around here. Okay? Alright, so this is the isobar map that I found for Australia on some specific date. It doesn't really matter which. Just the purpose here is to show you what the wind is going to be doing with respect to the pressure gradient. So again, this is in the southern hemisphere. So the wind is not being pushed 45 degrees to the right, but it's going to be pushed rather 45 degrees to the left. Okay? So if, let's see, I'm going to insert some arrows here to show you wind direction. If I'm looking at Perth, for example, as that location, you see that the pressure gradient goes from high pressure down here to low pressure up here. And so the pressure gradient is simply from south to north. However, remember that the Coriolis force is going to push it 45 degrees to the left. So that means that the wind direction is going to be rather from the southeast to the northwest. So I'm going to insert maybe an arrow pointing that way, which is about 45 degrees, right? Make it big. Cool. So, which means that the wind direction is coming from the southeast. So that would be the answer for that one. If this was located in the northern hemisphere, then the wind direction would be 45 degrees to the right, which would change this coming in from the southwest, right? But it's in the east, or sorry, it's in the southern hemisphere, so it's going to be the opposite. Cool. When we look at Sydney, same thing is happening. You have high pressures to the south, low pressures to the north, so wind is going to be deflected 45 degrees to the left, so the pressure gradient, or sorry, the wind direction is going to be coming in also, from about the southeast. Lastly, when we look at Darwin, we have that the pressure goes from high up here on the kind of eastern part to lower down here in the western part, which means that the wind, as it's deflected to the left, is going to be coming in kind of from the northeast to the southwest, right? So next to these, I'm also going to go ahead and add the pressure gradient so that it's clearer to you. The pressure gradient is going to be in red, and the wind direction here in blue. So that's the pressure gradient for Perth. This is the pressure gradient from Sydney, more or less. This is more or less a pressure gradient for Darwin, kind of. So maybe this should be deflected a little bit. Alright, so again, this is just how you do it. Remember that this is in the southern hemisphere, so wind direction is opposite direction. So as you're doing your map from the actual lab, take that into account, okay? Alright, so I'm also going to go ahead and skip this instruction part. Here I'm mostly just going to help you on how to look for things on Google Earth if you've never done so. And otherwise look at the different images that I have for you on the presentation on PowerPoint. So if you have Google Earth, go ahead and open it. So what you're going to look for here, oh, let me make this bigger for you. What you're going to look for here is Greensburg, Kansas. Here on the search bar, so go ahead and look for it. It will take you right to it. Great. So now you see how that is currently. This is now, okay? And you can also go ahead and add imagery date. So here on the bottom left, this has historical images starting in 1996. So each of these little points, or rather segments, represents a date when a picture was taken. So on the lab, I believe that I asked you to look at 2004, and then later at 2007 and 2006, and the differences between those two, basically. So in 2007, May of 2007 is when the tornado occurred. So basically doing that as well as measuring. So here's a measuring short ruler, basically, and you can use whatever unit you want, and then record a distance from there to there, for example. You'll get a different distance shown. So that's the three main options, or the three main tools that you need to use for Google Earth for this specific lab. If you don't want to download Google Earth, or if you just find it too hard, or don't have the capability with your computer, I also have a document to help you with that. So let me show you that. So this document here is also from Blackboard. You can also download it right from there, and it has the necessary images that you need in order to complete this lab. So I have the dates spelled out right here. So for example, this was taken October of 2017, and here I have a measuring scale of how large that specific distance is. This is August of 2006. Alright, same distance spelled out right here. This is May of 2007, and the same distance spelled out right there. They're all up to the same, or pretty much the same location, okay? And that's it pretty much, I think. Yeah. So if you don't want to download Google Earth, those images should give you enough to visualize what you need to finish for on this lab. But if you want to, please go ahead and download Google Earth. It's super cool to go ahead and play it with it. And I think it becomes useful for the next lab as well. Alright, so with that, I'm going to go ahead and go back to part 2 of the lab, which was the extra credit part. I believe that everything, once you have those images or Google Earth, everything from questions 14 through 17 is fairly straightforward, so you should be able to answer it without any issues. So I'm going to go back to part 2 and help you out with what it is that you need to do in this section, which it can be a little bit tricky. Okay, so the second part, which again is extra credit, has to do with orographic lifting, and it relates a lot of the concepts that we learned in the first part, a lot about the relative humidity with it, okay? So I'm going to go ahead and skip through these first part, this introduction part, and just jump in right to the questions. So this is the diagram that will help you kind of put things into perspective, and it shows you Seattle here to the west and Ellensburg here to the right, or to the east, I should say. The first one being to the west of the Cascade Mountain Range, and then the second one being to the east of the Cascade Mountain Range. So the parcel of air is dry. So there's a parcel of air that's coming from the west, as you're seeing here in the image, and at this point it is dry. when it hits the Cascade Mountains, so as it's moving to the east, sorry, it begins to rise, right? Because it has to go from here, the sea, basically up through the mountains, and then eventually make it to the eastern part of the country. So, as it's rising, it cools at a constant rate of 10 degrees Celsius for every kilometer that it rises vertically. So remember, a kilometer is 1,000 meters, okay? So here you have 500 meters, 1,000 meters, 1,500 meters, 2,000 meters, 2,500 meters. That's pretty much as high as the Cascade Mountains get. Okay, so this is a dry adiabatic or adiabatic lapse rate, okay? So the lapse rate, meaning the rate at which it cools, is called an adiabatic lapse rate, and it's dry. It differs from the wet, as we'll see later. So if the parcel of air starts at 20 degrees Celsius at sea, so here it's at 20 degrees Celsius, determine the temperature of the parcel for each elevation below. So if it changes 10 degrees Celsius for each kilometer that it goes up vertically, what's it going to be at 500 meter elevation? What's it going to be at 1,000 meter elevation? And at 1,500 meter elevation. So I'll do one of these three for you. So basically, if I know that it loses 10 degrees Celsius every kilometer that it rises, I know that it's going to go from 20 degrees C to 10 degrees C in 1 kilometer. So at 1,000 meters, this will be 10 degrees C. Okay? Cool. I'll let you figure out the other two. All right. Number 2 has to deal with what you guys did for this chart right here. So whatever the relationship was between temperature and relative humidity, whatever you found it to be, will be useful again when you answer question 2. Okay, so yeah, that will be what you use. Question 3 and question 4 are kind of based off also from the first part of the chapter of the lab. So make sure that you review that before you answer them. All right, and then question 5 here says, because condensation is occurring as the parcel of air continues to rise, remember condensation is when there is a phase change, right? It goes from being gaseous or vapor water to being liquid water. As it continues to rise and be forced over the mountains, the parcel of air is now moist. So it's no longer a dry adiabatic lapse rate, it's no longer dry, but it's moist because there's starting to be a change in phases. So what happens with that rising as a moist air parcel is that it now cools at a slower rate as it continues to rise. So it no longer cools at 10 degrees Celsius per kilometer, but it's going to cool at 15 degrees Celsius per kilometer. So based on that new lapse rate, record the temperature of the air at these two new temperatures. So I'm not going to go ahead and do it because I think you guys probably can do it on your own. But basically it was at X degrees Celsius at 1500. As it rises another 500 meters, what's it going to be at if it only changes 6 degrees Celsius per kilometer? Okay? So I'll let you figure these two out, and that should help you. Number 6 kind of goes hand in hand with number 5. Okay. Number 7, it also goes hand in hand with number 5 and 6. Number 8 here also takes into account the chart that you made up here, the relationship between the temperature and the relative humidity, just so you know. And then number 9 has to do a little bit with logic, but a little bit with what you did on number 5 and number 1. So think about that. And then here, after you have thought about number 9, whether you think that the air parcel is going to be dry or moist on the east side of the Cascades, you're going to also determine the lapse rate for the air parcel as it's heating up now. Not as it's cooling down, but as it's heating up. The same way that you did the other couple exercises on number 5 and number 1. So I think you guys can do it. It's not terribly hard. If you need any help, as always, you can come to me. But I'm going to leave it as that. Again, this whole part 2, is extra credit. So you don't need to do it, but it's a few, I think, relatively easy points for you to get. So good luck.